In the previous section, we used the telephone model to calculate future state probabilities and determine its long-run behavior. All of those calculations relied on one central statement. The future depends only on the present state. So far, we have treated that as an intuitive description. Now we will prove it mathematically. This proof explains why the entire past can be replaced by one current state. Let Z0, Z1, Z2, and so on represent the telephone's state at successive times. 0 means free, 1 means busy. A complete history might look like 0, 1, 1, 0, 1, 1, 1. Suppose the final 1 is the telephone's current state. We want to compare two predictions. One prediction uses the complete history. The other uses only the current state. The formal Markov property says that the probability of the next state, given the entire history, equals the probability of the next state given only the present state. The expression on the left uses every observed state from time 0 through time n. The expression on the right uses only Sn, the state occupied now. To prove that the telephone process is Markovian, we must show that these probabilities agree for every possible history that has positive probability. The proof begins with the probability of an entire path. Consider the path free, free, busy, busy, free. Its probability is found by multiplying the probability of the starting state by the probability of each transition. We start with μ0 of 0. We then multiply by 1 minus p, 1 minus q, and q. More generally, the probability of a path is the initial state probability multiplied by all the one-step transition probabilities along that path. A long history is therefore constructed from simple local steps. Now apply the definition of conditional probability. The probability of the next state given the entire history is a ratio. The numerator is the probability that the history and the next state all occur. The denominator is the probability of the history itself. Using the path formula, the numerator equals the probability of the past and present multiplied by one final transition probability. That final factor is p of Sn plus 1, given Sn. The same past and present probability appears in the denominator, so it cancels. Everything before the current state disappears. Only the transition from the present state to the next state remains. That cancellation is the mathematical reason the telephone chain is memoryless. Return to the history. 0, 1, 1, 0, 1, 1, 1. The telephone is currently busy. The probability that it becomes free next minute is Q. Knowing the entire sequence gives exactly the same answer as knowing only that the phone is busy now. The earlier history does not improve the next step prediction. The present state is therefore a sufficient summary of everything relevant from the past. Without the Markov property, prediction might require storing every possible history. The number of histories grows rapidly with time. But with the Markov property, all of that complexity collapses into the current state and a transition matrix. For the telephone model, we replace a potentially enormous historical record with only 2 states and 4 transition probabilities. This reduction is what makes large random systems mathematically manageable. This proof also explains why the methods from the previous section work. Because the current state contains everything needed for the next transition, the transition matrix can update the probability distribution one step at a time. Repeated multiplication produces multi-step forecasts, And those forecasts allow us to study how quickly the system forgets its initial state and approaches its stationary distribution. The recurrence relation, matrix powers, and long-run probabilities all rest on the Markov property. There is an important limitation. The Markov property is a modeling assumption. Our telephone model assumes that if the phone is busy now, the chance that the call ends next minute is always Q. It does not matter whether the call began 1 minute ago or 20 minutes ago. A real telephone system might behave differently. A call that has already lasted a long time may have a different probability of ending soon. In that situation, the state busy does not contain enough information. We may need to enlarge the state to include the call duration. The system may then become Markovian in this richer state space. The same issue appears in applications. In a financial regime model, today's bull or bear state may summarize the information used to predict tomorrow's regime, but real financial markets may depend on additional variables. In a simplified quantum optics population model, the current ground or excited state may determine the next transition, but phase coherence or environmental memory may require a density matrix or an enlarged description. A process is Markovian only relative to a state description that contains enough information. The heart of the proof is one cancellation. The probability of the past and present appears in both the numerator and the denominator. Once it cancels, only the transition from the current state to the next state remains. This transforms the informal statement, "the future depends only on the present," into a precise mathematical result. And from that result come path probabilities, transition matrices, multi-step forecasts, and stationary distributions. The present replaces the past because, in a Markov model, it contains everything needed for the next prediction.